Hello everyone, my name is Afonso Fernandes and I will be presenting this talk on verification and visualization of a consensus algorithm using TLA+. The work I will be presenting was done during my master thesis at University of Porto in Portugal. First, I will talk about where this thesis theme came from. The initial thesis theme was Byzantine distributed storage, where the goal was to prototype a distributed storage solution that could tolerate Byzantine failures. The idea was to do it on top of Ceph, which is a well-known distributed storage solution that is open source and can tolerate crash type failures. The idea was to change how the Ceph worked so it could also tolerate Byzantine failures. The first step was to research about distributed systems and Ceph. I found out that Ceph uses a consensus algorithm that is based on Paxos. They mentioned some deviations from the original algorithm, and the main documentation of the algorithm was in the source code comments. Then my next step was to research about distributed consensus. For that, one of the main resources I used was the TL+ video course, where Ledis and Porta explains the TL+ language, and one of the examples he gives is for the Paxos algorithm. I found out having a specification helps in understanding the algorithm, as it gives clarity of the action that the algorithm can take, and also gives a way of exploring executions of the algorithm using the model checker. You can see how the value of the variables can change and how that values impact on the decisions the algorithm can take. So, as I found the idea very interesting, I proposed a new theme to my supervisor of formal verification of the Ceph consensus algorithm, where I will develop a specification for the implementation they have of a consensus algorithm. And the main objectives will be to have a better documentation of how the algorithm worked, do safety verification of the consensus algorithm that was implemented, because they mentioned some deviations from the original algorithm, and having a new way, and in my opinion an easier way of testing other versions of the algorithm, for example a version where Ceph can also tolerate Byzantine failures. In this presentation I'll start by presenting some background on what is the problem of distributed consensus, and I'll explain briefly how the Paxos algorithm works. Then I'll be presenting briefly how Ceph works and the specification that was developed for the consensus algorithm that is implemented. Then I'll present the visualization tool that was developed alongside the specification to help understand and explore the algorithm. Then I'll presenting some results on the performance of the specification and on the performance of the visualization tool, and I will end by presenting some ideas for future work. So, what is the problem of distributed consensus? Distributed consensus can be defined as a problem of multiple nodes agreeing on a sequence of values. Normally, this is the definition of the general consensus problem, and there is also a single value consensus problem. In single value consensus, we only require that the nodes agree on a single value. And then the general consensus can be obtained by multiple executions of the single value consensus. So if we can solve the single value consensus, we can solve the general consensus problem. Some important properties of the single value consensus. The chosen value must be a value from the set of proposed values. Only a single value must be chosen, and the correct node will only learn that a value was chosen if it actually has been chosen. One of the main algorithms to solve the consensus problem is called Paxos. Paxos is an algorithm that is crash fault tolerance, and I will first present the algorithm to solve the single value consensus and then Multi-Paxos to solve the general consensus problem. So Paxos works in a series of rounds. In each round there is a node that is elected as a leader, and you'll try to propose a value, and the rest of the nodes in the system will vote on that value, and if a majority of nodes vote on that value, the value is chosen. So normally it's divided in two phases. The first phase is a syncing or recovering phase, and the second phase is a committing phase. In the first phase, the leader starts by announcing a new round. This round has an identifier that is called ballot number and is represented by the variable b. Then the rest of the nodes of the system will reply with information about previous rounds. So if the leader was down in the previous round or it crashes, it has information about previous rounds. In the second phase, the leader will, using the information he received from his peers, he'll choose a new value to be proposed. That value can be a value from previous rounds if there was values proposed or chosen, or it can be a new value from the set of possible values. If a majority of nodes in the system agree on that value is chosen. A value can be chosen in multiple rounds, however, if two rounds have a chosen value, that value must be the same. Then Multi-Paxos, there is a new variable here, call it S, that will represent the slot in the sequence of values that the nodes will be agreeing on. Here we also have two executions of the second phase occurring one after the other to represent that the phase 1 only needs to occur once per round, and then the leader can propose multiple times. For example, here the leader thinks and changes information with his peers. Then he can, for example, propose a new value for the slot 1 of the sequence and then propose a new value for the slot 2. Now I will briefly talk about Ceph and present the specification that was developed for the consensus algorithm. So, as I talked before, Ceph is a distributed storage solution. That means that you can have multiple systems with storage, and Ceph unifies those systems so you can deliver a unified solution that can use all that storage. Here we have a simple diagram of the various components in Ceph. I'll mostly focus on these ones below. So you have object storage devices that are the components that will have the storage, such as hard drives or SSDs. Then the metadata server that will store metadata. The managers that will be responsible for monitoring the cluster. And you have monitors that are the main components on the context of this talk. The monitors will be responsible for maintaining a series of maps, and to keep track of the changes of these maps they use Paxos. So you have a sequence of changes that can be committed, and to know which changes to commit in each slot, they use the algorithm that is based on Paxos. For example, the monitor map will have information about which monitors are up and which monitors are down. These maps are important because Ceph uses an algorithm that is called crush, and this crush algorithm uses these maps to locate where the files are in the cluster. For the consensus algorithm, you can see here above the algorithm that is on Ceph and below the Paxos algorithm for comparison. The names of the phases are changes, but we can map the phases simply, so the operation collect and operation last can be mapped to the phase 1, and when operation begin, accept and commit can be mapped to phase 2. The implementation in Ceph is for Multi-Paxos, so we have also a slot variable. It's not called slot, but it can be a map slot variable. Also here in Ceph, the phase 2b is separated into phases, operation accept and operation commit. So there is no need for the peers to broadcast their votes. The leader is responsible for counting the votes and then transmitting that information to the nodes in the system. There is also a list phase not represented in this diagram, and this list phase has two goals. The first one to work as an R-tweet, so the leader can know which servers are up and which servers are down, and also works as a mechanism for the clients to know when it's safe to read a value from a monitor and when it's not. For example, at the beginning of an round, the monitors will be in a recovering state, so it is not safe to read a value. When the recovering phase ends, the monitors will enter an active state. In this active state, the monitors are safe to read the value that is there. And then, when a committing state starts, the monitors enter a committing state, and they are marked as not safe to read the value. And when the committing phase ends, the monitors are again marked as a state active by this list phase, and they are again safe to read the values that they have. Now I'll start talking about the specification. So before writing it, what I did was analyze the implementation and identify what mechanisms I need to abstract, and for those mechanisms, what were the properties that I would need to maintain so I don't find bugs in the specification that are not mapped to real bugs in the implementation. So for example, the communication mechanism. In the implementation, they have a complex mechanism based on TCP protocol. However, in the specification, it didn't make sense to model it in the entirety. So there is a simplified mechanism in the specification that has no message duplication. The messages are delivered in order for a given connection, and the messages are only discarded when a new election period starts. So an epoch is an election period. For the election logic, there is only one leader elected per epoch, and the quorum in the election will be formed with all available monitors, all the monitors that are not garage. For the failure model, I have two options: to do it implicit by letting the model checker find behaviors where the monitors don't respond, or doing it explicitly by having a variable that keeps track of which monitors are down and which monitors are online. I chose the second option, so I have a variable that keeps track of which monitors are available and which monitors are down, and when a monitor crashes or recovers, that triggers immediately a new election. Finally, for the transactions, this is which changes of variables are committed in each slot of the sequence of changes. In the implementation, a transaction can have a set of changes to multiple variables. However, in the specification, a monitor only keeps track of a single variable, so a transaction will only have a change to that variable. And the values in the implementation can be requested to any monitor, and if that monitor is not a leader, you will forward to the leader. However, in the specification, a change can only be requested to the current leader of the epoch. Before I show the specification, I'll just give a little overview of the various sections that are present in the specification. So at the beginning we have declaration of constants and variables, some initial definitions for variable initialization, message manipulation definitions, helpers, then the main algorithm separated by the list phase, the commit phase, collect phase, and also the client requests, the leader election, then definition for crash and recover, the dispatchers and the next statement, and at the end also have safety properties that are called invariants. The specification is open source on this URL for my GitHub. I'll go over there. So in the GitHub we have these files. The main file for the specification is here in the source folder. Here in the source folder I have the configuration, the PDF, and the main specification for TLA. So in the configuration we have here declaration of the set of monitors, the set of values, then the names for the type of message, the state name, and names for each phase. These names here are the same as in the implementation. These are extra variable I added for specifying more easily the algorithm. Then in the TLA I'll like to first take attention to these types. I added type annotations using the syntax of the Appalachian type checker. These type notations can be checked using the type checker, but the main reason I add them is to have a better readability of the meaning of each variable. For example, here in this variable pending PN, we can see easily that this variable will track the proposal number for each monitor and not, for example, a global proposal number. So this variable is a function from monitors to proposal numbers. This proposal number is the identifier of the round, so it's the ballot number from the Paxos algorithm. This value version is the slot in the sequence of changes, so it can be up to that slot variable I have in the diagram. Then the value is the value that will be changed. This monitor store is a variable that the monitors keep track of, and the values is the sequence of changes that will be made to this variable. Then going a little below, we have here the definitions to exchange message. As I said before, the messages are modeled with some similarity to a TCP protocol, where if you have connections from two monitors, and to add a message will add a message to the end of a connection. To remove a message, as the messages are handled in order, we remove the message that is in the front. Here below we have some helper definitions. I'd like to point out this get a new proposal number definition that was used to compute the ballot number or proposal number of a round. So the one that is used in the implementation is this one above, where they use the rank of the monitor. This is basically identifier. For example, for the monitor 1 is the rank of the monitor will be 1, for monitor 2 the rank of the monitor will be 2. However, this definition makes the monitor set not symmetric, and that had many consequences on the performance of this specification. So I changed it to use the epoch variable instead of the rank of the monitor. To find that this was the definition that was breaking the symmetry was also a little hard. This specification is open source, so you can go a little deeper afterwards. I would like only to point out one or more two things. So here you have the leader election, here the crash and restore definitions to crash a monitor and restore a monitor. A monitor will only be crashed if there are enough monitors left to form a quorum. And there is this search space to limit the number of states that are explored in the model shaker. So here we use the epoch to limit the number of elections, the last commit to limit the number of commits of variables that are changed, and the accept pn to limit the number of rounds. The safety properties that were defined in this work are these two. They are linked with each other. So up here we have the same monitor store that states that when two monitors are in this state active, then the value of the variable they are keeping track with must be the same. So when they are in this state active is when clients can read the variable from the monitors, and that variable must be the same. The other safety property is this one below, that states that for each slot, so the version will be the slots, then there is a value where all monitors that have committed for that slot must have the same value committed. After defining these two safety properties, what I did was check in the specification to see if I could find any bug, and story short, I didn't find any. So what I did was introduce a bug in the specification. The bug I chose to introduce was this one, where the proposal number of the proposal that is being made is not safe. So when the monitor goes down and the leader tries to sync and recover information from previous rounds, you only have the version that was being committed and the value, and you'll not have the ballot number of that previous proposal. This bug was a bug that was present in the real implementation many years ago. I'll go over that now. So this is the commit that fixed that bug. It was before version 1.0, so very early version of Ceph. And if you introduce this, so you change these two lines in the specification and run in the TLC, we obtain an error. So this took around 50 seconds, 43 seconds, and produce an error trace of size 37. So it took 37 states to reach a state where there is a monitor. So we have here a monitor that has two values committed and they are different. So for monitor 1 it committed v1 and monitor 2 committed v2. As you can see here, it's a little difficult to understand what is happening, as there are too many states and each state has too much information. So I now switch to the visualization tool I created to help understand these trace errors, and also the main reason I created was for this Graph Explorer, but for now I use it for the Trace Explorer. So I already selected the error trace, and if I submit it, I have this interface with the current state and the next state. So you can go over the states, and as you can see, the leader is selected and he proposed the v1. Then the monitor 1 crashes and we go to monitor 2 is selected as a leader and he'll propose and commit the value 2. Then the monitor 2 will crash and the monitor 1 will be elected as a leader, and you'll now have to choose between proposing v1 and or proposing the value 2, proposing value 1 or value 2. As it doesn't have information of when those values were proposed, it only has information about for which slot and what was the value. It cannot choose between those two, and he ended up choosing v1, which will violate the safety property, as you can see here. Now I will present in more detail the visualization tool. So the main motivation to create the visualization tool was at the beginning I wanted to make the monitor set symmetric, and that was not happening. And the way I found out that was not happening is because of multiple executions of the model checker were giving me different numbers of distinct states that were being explored. So with model checker I could extract the state graph, and different executions were giving me different state graphs. So there were behaviors that were being explored in one state graph and not in the other, and that the main reason for that was the symmetry that was being defined. And I had to find those behaviors and compare and trying to understand why those behaviors were happening. To explore those state graphs, I didn't find any tool to helping me do that. The state graphs were very large, hard to open in my computer, and each state in state graph also had too much information. So I developed a simple tool that can be opened in a browser to explore these state graphs and see what the behaviors that are happening in these state graphs. Later on I also had the support for trace errors, as you see me use it before. So this tool can be used with the dot format and the trace error format from the TLC model checker. And the states can be personalized using JavaScript, HTML and CSS. And to help doing those personalization, there is a parser that translates a TLA expression to a JavaScript object. So the information in the state can be more easily accessed and used in the JavaScript. The visualization tool is open source and can be found on this URL. So if you go to the URL, you have here the repo where this visualization tool is, and here in the examples we have the various examples here of how to use the visualization tool. This is the default configuration without any personalization of the states. It only prints the pre-interpreted version of each state, and here with some graphics. So if you open that example, you have here 3 files that need to be changed. This first file is for the structure, so it can be mapped to the HTML, and it's an HTML. So you can see here there is the West Island, the block of water, the East Island, and then the printed version. And here below we have the template for an island where we have the boat, and the boat is composed of a sail and a base, and then the text field with the number of missionaries and the number of cannibals. So if you open it again, you can see here the island, the block of water, the island, and the boat that is composed of 2 components, and each island has 2 text fields. Then there is the CSS for personalization and colors and shapes, and the JavaScript to fill the information with the information that comes from the state variables. So the variables are parsed using this function, and then here below you count the number of cannibals and the number of missionaries. So if you go to the dot, you can see that the variable that is in the trace file is this one, so we have to count the number of C's and the number of M's to know the number of cannibals and the number of missionaries. Now I'll change to a little demo of the example tool. So I already selected the dot file and I will open. So you can here below also change the name of the next state that can be used. So if you open here Ceph constants, source and JavaScript, you can change the state identifier. There is also a function to change that, and here the state identifier is in the variable called step name. So we can go a little bit, choose which state is happening, crash. As you can see here, you can restore. Now there is options only to two of the monitors. This is because two of them are equal and we are using a symmetric set for the set of monitors. So only two options of electing a leader, and you can elect a leader. Here we can cannot go further because that is the reducer space definition that limits the number of states that are explored. So here we reach a limit. This is also because I couldn't upload files that were too large, so I upload a simpler example. And we can go to previous states and explore the state graph in this way. And that is it. Now I'll be presenting some performance results both on specification and on visualization tool. So here we have the number of states that are generated compared to the maximum epoch or the limit number of elections. As we can see, the number of states grows exponentially as expected, and I add a graph for various limits that are used. Here the number of rounds that can happen, the number of committed values, and the number of monitors. You can see that some variables have more impact than others in the number of states, and in all of them the growth is exponential. Then for the performance of the visualization tool, here I am analyzing the amount of memory that the tool is using. This is because at the beginning the tool was developed mainly to compare some state graphs, and those state graphs were a little large, so I needed to develop a tool that wouldn't load the entire file into memory, so for me to not go out of memory in the computer. So the tool is using around 10% of the entire file size. Here we have it comparing for a file with 500 megabytes, 1 gigabyte, 5 gigabytes, and 11 gigabytes, and it is more or less stable of the use of around 10% of the entire file size into memory. To finish the presentation, I will now present some future work ideas. So first, the idea to specify and test other versions of the consensus algorithm using as a base the specification that was developed. I have also here the idea of rewriting the Explorer tool in TLA+. So to do that, I have here some ideas. First, to create a state print model that takes, for example, the variables of the current state and a template file that can be a template for HTML, and fills the template with the variables and prints out to a file with a name that you can give. And this state print function can be called anywhere inside your specification, so it's easier to use and easier to manipulate, so you can call it only when certain conditions met. Then the files that are produced can be explored, for example, using a tool that can render multiple HTML files to be easier to explore them. I also have here a model to interactively explore the specification. I don't know how possible this is to do, but basically the idea would be to change out the behavior of the model checker. So the model checker explores the states that you give them, and for example you give the user the option to choose the next state from the possible next states, and change the model checker to explore only that state and then ask again, and also gives the option to go backwards and change the current state to a previous current state. I don't know how possible this is. It's an idea that I will try to explore later on. And if you want to reach out to me or contact me, you can do it on LinkedIn. And if you want to see my process, you can do it on GitHub. Thank you for your attention, and I hope you enjoy the talk.